So thank you very much. I really appreciate the invitation to come talk about our work here, and Brian has given a great introduction. So I'm going to tell you about a theory for the hidden order in uranium-2 silicon-2, which is basically prompted by this whole question of how can we have such a large jump in our specific heat but not see any observable order parameters. And so our proposal for the hidden order parameter is a type of order hybridization, where the hybridization is quite large, but due to the Cobb effect, all of the observable consequences end up being quite small. And this work was done with Premi Chandra and Piers Coleman at Rutgers, and we have a number of papers covering different aspects of this work. And I'm also going to show a little bit of nonlinear susceptibility data in a paper with Art Ramirez and Jen Trin that is currently under review at Purell. And we've had a lot of useful discussions with many people over the years. This work started when I was a postdoc at MIT, funded by the Science Foundation, and has been continued to be funded by my startup fund at Iowa State. So here is the overriding question, which Brian already presented, and people have been puzzled over for the past 30 years. We have this beautiful mean field like phase transition. If you integrate up the entropy, underneath that you get a large entropy. It depends how you subtract the phonons, so we say around 1/3 R log 2 as opposed to 0.2, but it's large. And you would expect a large moment associated with this large entropy. R log 2 comes from the fact that we have uraniums, which are local moments at high temperatures at least. So this leads to the question of what order parameter is it. And so I have a similar slide to Brian, because it's been an open question for over 30 years, and there's over 30 theories, and they keep coming out more and more interesting theories each year. And basically you start off thinking, well, it could be something simple like antiferromagnetism, some kind of density wave, and as those theories sort of ruled out, people got more and more interested in this problem because if it looks so simple, you have this beautiful, huge transition, we must be sort of missing something big. And so it's led to a lot of interesting theories, and even if they're not necessarily correct for uranium-2 silicon-2, it's really been a great driving force for theory over the past 30 years. So if it looks so straightforward, the question is, are we missing something fundamental? We have what we think is a very interesting sort of fundamentally new type of order. And whenever you look at an order parameter, you sort of want to know what is the broken symmetry and what is your order parameter. And so I'll show you that we're going to propose something that breaks reversible symmetry and is basically a spinorial type of hybridization. But I want to sort of go back through some of the data that Brian presented about uranium-2 silicon-2. And of course, whenever a theorist presents these things, it's biased from their particular view of their theory. So this is sort of going to lead you through the reasons why we developed this particular type of theory. So here's the magnetic susceptibility. At high temperatures, you see you have basically free ioning moments with a Curie-like susceptibility. And so this looks like a condor lattice where the uraniums are carrying an ioning moment. And then as you go below the coherence temperature of around 70 Kelvin, these moments are quenched. Your electrons get slightly heavy, but there's still plenty of entropy left, so that you can have this 1/3 R log 2 condensing at the order temperature. So clearly this kind of hybridization is important to the problem. It's clearly not complete by the time we get to hidden order. So we see this mean field like phase transition at 17.5 Kelvin. Under pressure, become antiferromagnetic. Under field, you favor this hidden order over the antiferromagnetism, but is very slowly killed by the magnetic field. It persists out to 3540 Tesla, where you have various possible quantum critical points. And as Brian told you quite a lot about, you can get very interesting phase diagrams under doping. So one of the most interesting points, and I'll come back to this because it's very important, is that when you develop these heavy quasiparticles in your hidden order, they actually inherit the ioning nature of your high temperature moments. And this is seen by measuring the angular dependent G factor from the phosphon alpha, and also by looking at the Cooper pairs that develop in superconductivity of their HC2, similarly anisotropic. There's also indications that this hidden order breaks tetragonal symmetry, so indications from torque magnetometry, which show that you develop a chi-xy at the hidden order temperatures. There's been some measurements that see a small orthorhombic signature of the hidden order temperature. Again, much too small to explain the large amount of entropy. And there's also some of the plaster resistivity measurements from Ian Fisher's group, which indicates a two-component order parameter, which would couple to nematicity. And finally, there's superconductivity at 1.5 Kelvin, which is a very interesting problem in itself, and I won't touch upon it, but it's probably due to asymmetric pairing. There's some indication of time reversal symmetry breaking, and again, these heavy closet particles. So, broken tetragonal symmetry we know about the hidden order. There's indications that there might be broken time reversal symmetry. So the first sort of comes by looking at this phase diagram, and it looks like basically antiferromagnetism and hidden order can be related by some kind of rotation in an internal parameter space. And this is sort of backed up. If you look at the longitudinal spin fluctuations as you come into the hidden order, these would be the fluctuations into the antiferromagnetic state. Those get very soft, but not quite critical as you come down to hidden order, which indicates that maybe you're coming down to something that has a choice between hidden order and antiferromagnetism, and this could be some kind of pseudo-Goldstone mode between these two phases. And if that's the case, if there's a really related by this kind of adiabatic continuity, and there's a pseudo-Goldstone mode, since antiferromagnetism breaks time reversal symmetry, so must the hidden order. This is very indirect. This presence of the chi-xy can also be interpreted to suggest broken time reversal symmetry. Basically, if you want to explain this chi-xy, you need to carve the following Feynman diagram, and it's coming from conduction electrons scattering off of the hidden order. So you can write this as sort of a T-matrix scattering, and your T-matrix has this general phenomenological form, where H has to be proportional to a sigma x plus sigma y times some sort of form factor in momentum space. So if you assume that this is a very large effect, the relative ratio between chi-xy and chi-xx is around 10. And so it's very natural to explain this in terms of a resonant scattering off of the F electrons as opposed to sort of scattering off of some kind of itinerant density wave where it would be very difficult to explain this large magnitude. So in that case, you can write your T-matrix as sort of an F electron scattering, and so this means that it has to, this form factor has to preserve invergent symmetry, and therefore it has to break time reversal symmetry. So again, very indirect, but a possible, another possible break of symmetry associated with this hidden order phase. And then the gaps in the system are very interesting. We see from thermodynamics of transport that most of the Fermi surface, or 40% of the Fermi surface, gaps up at the hidden order, like a density wave. You can pull out from the specific heat a gap of around 4 MeV. If you look at STM, using quasi-particle interference, they can measure the band structure effectively, and that shows a hybridization gap that's developing at T hidden order. And the magnitude of that gap is also around 4 MeV. So I'm going to show you. Here is first a theoretical picture, just to remind you of what the development of a hybridization gap looks like. At high temperatures, one has a conduction electron band and a flat F band. And once they hybridize, they have hybridized together here, so you have this kind of band bending, very strong band bending in your Fermi surface. And what's really interesting about this STM results is as opposed to this hybridization gap developing gradually as a crossover, as one normally sees in Kondo systems, it develops sharply at the hidden order transition. So now I'm going to show you, oh, sorry, this is not showing. No. Sorry, I must have. Okay, I'm sorry, I didn't push you on. So I apologize, but there should be a slide showing basically you see this conduction band and then you see this band of developing in the STM. And you should also see references to Schmidt and Vivian. This is the gap that they pulled out. That so, alright, so you see this STM gap. The same gap is also seen in optical conductivity. where they actually see a gap developing at T in order, but another gap also develops at around 50 Kelvin. Point contact spectroscopy sees gaps developing at different temperatures, depending on the group doing the measurements. There's also some indications of a pseudogap. So sort of the interesting conclusion from this is that we actually see multiple gaps developing at multiple temperatures, some at high temperatures, and some at the hidden order. And the most interesting point for our theory purposes is that the hidden order gap actually appears to be a hybridization gap. And there's also various indications from our tests that this coherent formy liquid is developing at T hidden order. Okay, so as a theorist, we want to sort of address, as we develop our microscopic theory, we want to address a couple of questions. So the first question we might consider when looking at uranium is it local or itinerant physics, or some combination of the two? And if it's local physics, you must further resolve what is the actual electron valence you want to start with. Is it 5F2 or 5F3? And once you've had one of those, then you further resolve it to look at your crystal field levels, where there's sort of older theories propose different quadrupolar and octopolar ordering of these crystal field levels. There's a recent theory by Holiday and Collier showing basically if you have two singlet levels, it can develop a hexadecapolar order. And the gamma-5 doublet ground state, which was originally proposed by Metzger, is a doublet that we then use to develop our theory of Hastatic order. You can also look at basically itinerant physics, where you get various density waves, and then there's different combinations between the two, which you'll hear more about later in the session. All right, so let me return to this giant Ising anisotropy, as this is sort of the thing that, as we were developing this theory, we found the most interesting. So we know from the magnetic susceptibility that our uranium moments are very strongly Ising-like. So when we calculate the expectation value of J plus or minus, this gives us 0. And this is actually very difficult to find if you have a 5F3, because sort of generically you will get some expectation value of this, and so you can have anisotropic moments, but to have them be perfectly Ising-like is extremely unlikely. It's basically some tiny point in parameter space. So to us, this indicates that you likely have a non-Kramers doublet ground state, which gives you this natural Ising anisotropy where you have a 5F2 state. And what's interesting is not only are the uranium moments severely Ising-like, but if you look at the conduction electrons, which you can do by just looking at the Hastatic, which measures conduction electron magnetization, these also seem to inherit this Ising nature. So you can basically, by doing the Hastatic and tilting the magnetic field, you can pull out the G factor, and it fits perfectly this cosine beta anisotropy, which you get from Ising magnetic moments. So what we have is, we can naturally think of this as just a heavy electron that has perfect Ising symmetry, and this comes from hybridizing with this 5F2 non-Kramers doublet. So at this point, this seems fairly straightforward, but actually this is very interesting because it's all kinds of new effects if we look at basically the consequences of hybridizing with a non-Kramers doublet. So basically the difference between Kramers and non-Kramers is the difference between half-integer spins and integer spins. These behave differently under time reversal, specifically under double time reversal. So you take an integer spin, you apply time reversal twice, you get back to the same wave function. You take a half-integer spin, you apply time reversal twice, your wave function picks up a minus sign, and you have to apply time reversal 4 times to get back to your original state. And so if we have a hybridization between a local moment, which is non-Kramers, and so has time reversal squared, giving me back the same state with no phase factors, and I have conduction electrons, which are spin 1/2, and therefore are Kramers-like, and you pick up a minus sign under double time reversal. When I look at their hybridization, just sort of a naive hybridization, I can look at how this Hamiltonian behaves under double time reversal, and I know what this conduction electron state does, I know what my local moment state does. What I don't know is what my hybridization does, but I do know that my Hamiltonian has to be invariant under double time reversal. So this tells me that my hybridization actually has to pick up a minus sign under double time reversal state. And so it is going to break time reversal symmetry just like a spinner. And so basically it breaks time reversal and double time reversal symmetry. And this is not that surprising if you think of this hybridization as essentially mixing a half-integer spin state with an integer spin state. That mixing has to carry out an integer spin somehow. So to get more into the theory, let me first sort of review the theorist's picture of a typical hybridization process or typical condo effect. So you have a Cramer's doublet ground state, say a 5F1 configuration, and it can flip its spin by fluctuating the virtual valence fluctuation to a singlet excited state. And this could be 5F0, there's really just one state there. As theorists, we represent, treating this within an Anderson model, we would represent the state with a single slave boson, which we call B. And effectively, this excited singlet carries no quantum numbers. The hybridization will break no symmetry, so it's going to develop with a crossover. And so if I plot it versus temperature, my hybridization gap will start turning on at high temperatures, and we'll just have some sort of crossover scale associated with it. However, when I look at how a non-Cramer's doublet can flip its spin via virtual valence fluctuation, it's going to go from a 5F2, which has an even number of F electrons, to a 5F1, which has an odd number of F electrons, and therefore must be a doublet protected by time reversal symmetry. So you essentially have a non-Cramer's doublet fluctuating to a Cramer's doublet excited state. And so now, if I want to represent this excited state, I actually have to introduce two slave bosons, which are packaged together into a spinner, one for sort of the up state and one for the down state. And so my excited Cramer's doublet is actually carrying a magnetic quantum number, and when I develop hybridization, which I treat as condensing this slave boson, it's going to actually break time reversal symmetry. And therefore, if I have a hybridization that of a non-Cramer's doublet, it has to break time reversal symmetry and develop into phase transition. And so then it's not surprising to get this kind of behavior where your hybridization gap would be turning on sharply at the in-order temperature. So if I sort of think of this as a spinner, the spinner can point anywhere in SC2 space, and so it can it can require an amplitude, and then it also has to require orientation, and that's the part that breaks symmetry. So it turns out when we look at the specific microscopic theory, if this hybridization spinner points along the c-axis, we get a state that looks a lot like the antiferromagnetic phase of uranium ruthenium 2 silicon 2. And here I'm explicitly putting in the staggered Q vector that we know the order obeys. However, if I put my hybridization spinner in the plane, I actually get a phase that doesn't have any large moments and is surprisingly similar to what is observed in uranium ruthenium 2 silicon 2. And so this is the phase that we call Hastatic order, basically because this spinner has developed a orientation, and so this is our sort of proposal of what the hidden order is. This is development of a hybridization spinner. So when we have this theory, one can sort of first do a Landau theory to look at what happens when we have a spinorial order parameter. Here's our order parameter psi. Here's this sort of straightforward Landau theory that one gets for any order parameter. And one can then add basically a parameter lambda, which will tune us between our hybridization spinner pointing along the c-axis and the hybridization spinner pointing in the plane. And so this very naturally gives us a phase diagram that roughly resembles the phase diagram of uranium ruthenium 2 silicon 2 under pressure, where this transition from a hybridization spinner in plane to out of plane is essentially a spin flap transition. One of the neat things that comes out of this is if you take the hidden order phase and you look at the gap to longitudinal spin fluctuations, this actually is suppressed to 0 at this first order phase transition. And so this with this sort of characteristics for behavior, so this is something that would be very interesting to look at, say, in the iron-doped uranium 2 silicon 2, where one can actually go through this pressure and measure this gap with inelastic neutron scattering. Another interesting thing comes out of this Landau theory is if you look at the nonlinear susceptibility. So the nonlinear susceptibility is the coefficient of this sort of B cubed term in the magnetization, and it was shown back in 1992 that this has an anomaly that looks very much like the specific heat anomaly that develops at the hidden order transition. And it's seen sort of along the c-axis, and nothing was seen in the plane where the signal is much smaller. So if you look at the Landau theory, basically because your alpha electron is only coupled to the Z component of the magnetic field, you get a Bz squared term that couples to Lorentz parameter squared. And so if you go through and take your four derivatives of your free energy, what you find is that you have a cosine to the fourth theta and isotropy of this nonlinear susceptibility. And so this is one of the predictions of our theories, that you would have this basically a more than 1,000-fold anisotropy of this nonlinear susceptibility, this jump in the nonlinear susceptibility, so this jump right here. And this is a paper that should be coming out pretty soon with Gentrin and Art Ramirez at UC Santa Cruz, where they measured the nonlinear susceptibility jump and actually the nonlinear susceptibility at different temperatures. And so here is the nonlinear susceptibility jump, which fits very well with this cosine to the fourth theta. Here is the linear susceptibility, which goes as cosine to squared theta, as one would expect for an Ising magnetic moment. Okay. So this is sort of a nice consistency check. So now I want to go to look at to look again at this in more detail and look at a microscopic theory. So we said the important characteristic is that we have a non-converse doublet in uranium with 82 silicon 2, which is in tetragonal symmetry. The non-converse doublet is going to be a gamma-5 doublet. So it's a mixture of the JZ is plus or minus 3 and minus or plus 1 states. So this is doublet. It's protected by tetragonal symmetry. If I break the symmetry, go to an orthorhombic state, this becomes 2 singlets. It is magnetic along the z-axis and quadrupolar in the plane, so it's an Ising doublet. And if we take this non-converse doublet and then we go and we develop an Anderson model, we basically the symmetry of this non-converse doublet very strongly constrains the nature of our valence fluctuations. So we can take this non-converse doublet and straightforwardly write down a valence fluctuation term and then proceed to solve it. So, okay, so if you're not familiar with crystal field theory, you can sort of ignore the particular gammas. Basically, we have this symmetry, and it says that we hybridize with conduction electrons that have two different shapes over the F electron site, which are given by these two vectors. And so if we write a hybridization term, so this is written in terms of Hubbard operators, where I destroy this state, create this state, and create a conduction electron with some particular symmetry, I'll get two different terms, and the signs sort of come out from the gamma-5 doublet. And so I can take this hybridization term along with all the other terms in my Anderson model and proceed to solve it. And the way we do that is by introducing slave bosons and fermions, as I sort of indicated before, to represent the doublets that are in our system. So I can represent this ground state doublet with a slave fermion, which is this chi alpha, and I can represent my excited doublet with now a slave boson, which is this psi sigma. And so these Hubbard operators that take me to states are now bilinear terms where I annihilate one fermion and create a boson. So what's sort of interesting in the system is that I have a number of different types of moments. I have my local moment, which is my quadrupolar in the plane and Ising out of the plane, which is just chi dagger sigma chi. I have a mixed valent moment, essentially when I start to occupy this excited state, I develop a tiny spinner, a tiny moment, which is my hybridization spinner, and that can have an orientation and has a physical moment associated with it. And I can also have conduction electron moments. So I'm going to skip. Okay, so once one does this, there's a lot of manipulation that I'm happy to discuss with you afterwards if people have questions. But what one ends up with is a valence fluctuation term where I have two different types of hybridization, and I've picked a particular gauge where the hybridization in channel 6 is uniform and the hybridization in channel 7 is staggered. This is a gauge choice. What I can really look at whenever I do a measurement is something like a V dagger V term, and so within each channel, the inter-channel hybridization gaps that I'm looking at are going to be uniform, and if I go back to my slave boson, these will basically be proportional to the amplitude of my slave boson. Whereas if I look at the inter-channeled hybridization gaps, this is actually going to be a staggered hybridization gap, and it's going to be proportional to the moment of the hybridization spinner. And this term actually breaks, is a term that actually breaks time reversal symmetry, and actually you can see that it's breaking tetragonal symmetry as well. However, it's doing it with this is a D-wave form factor where the orange is and blue are different signs. So this term breaks the symmetries, while this term is not necessarily breaking the symmetries. Okay, so this is the theory. Okay, great. So then I can go and look at the consequences of this theory. So the first thing we want to look at is the moments, because sort of the defining characteristic of hidden order is that there are no large moments. So as I said before, there are three types of moments. There's local moments, mixed valent, and conduction electrons. So let's start with the conduction electrons, which we can calculate explicitly. And we find that it does develop a small conduction electron moment as I go below the hidden order. It's of course staggered, just like the hidden order itself, and it points in the plane. And the interesting thing about this moment is that it's very, very small. And the smallness is enforced by the fact that this comes from the Kondo effect. So this is from Claxton-Anderson. Basically, the moment is limited by the order of the Kondo temperature divided by the bandwidth, which is around 1/30. If we calculate this, where this is a calculation that includes not only the conduction electron moment, but also this expectation of the 5F1, this mixed valent moment. And this is a particular computation where we put in about 20% mixed valency. This is not really known. There's a number of measurements, but the true degree of mixed valency in silicon-2 is still up in the air. And we get a prediction of around 0.01 magnetons. Okay. So this is our conduction electrons. This is quite small and in the plane. And if I now look at my local moments, I can calculate the form factors of my two types of moments, my in-plane moments and my out-of-plane moments, and they both have D-wave form factors, and so I'm not going to get any magnetic or quadrupolar moments from my local moments. So there's no F-electron moments. That's good because these would be the large moments. Okay. I can then look for this broken tetragonal symmetry, and we can calculate this chi-xy, and this pops out. So this is the particular magnetic torque measurements from Matsuda's group, and the black line is our calculation. I wouldn't pay too much attention to how well it fits, since we have all of three parameters. What is, I think, characteristic is that we can explain the magnitude quite easily, and the nature in which it turns on sort of a t minus t in order squared. We also have an anisotropic hybridization gap with this sort of D-wave form factor. So this can explain some of these indications of tetragonal symmetry breaking, from cyclotron resonance, from these tiny X-ray signals, which are clearly not in the first order quadrupolar moment, but could come around as a second order effect. We also have a prediction of an energy-dependent pneumaticity that can be looked at in scan microscopy. So there's sort of a good consistency with a number of measurements for uranium, ruthenium, silicon-2. And so to sort of summarize, some of the most important experimental consequences that come out of this theory of hastatic order, we can very naturally explain the G-factor anisotropy. This is not surprising because that was basically the ingredient into our theory. We also explain this nonlinear susceptibility anomaly anisotropy, and we have this prediction for longitudinal spin fluctuations. Okay, so the last thing I want to talk about before I get to my conclusions is, okay, I told you before that there are multiple hybridization gaps in the system, so if everything is turning on hidden order, how can we explain that? And here I showed you before that we have two types of hybridization gaps. Intra-channel gaps that are uniform, they break no symmetries, and they basically correspond to the amplitude of this hybridization spinner. And then we have this inter-channel gap that is staggered, it breaks translation symmetry, it breaks rotational symmetry, it breaks time reversal symmetry, and it's proportional to the direction of the spinner. And so if we go beyond mean field theory, these two things don't have to develop at the same temperatures, and since these don't break any symmetries, this amplitude can develop at a higher temperature. And so our sort of proposal is that Hastatic order melts via phase fluctuations, where basically below the hidden order you have all of this, but above hidden order you can still have these kind of basically a pseudo-gap behavior, and that can explain the high temperature hybridization gap. It can also explain the formation of an incoherent heavy Fermi liquid. This is an older version of the slide. I can explain the heavy mass. And the key feature is that you do have to have a hybridization gap that turns on the hidden order. It just doesn't have to be the only hybridization gap. So to conclude, our main contention is that this observation of these very Ising-like quasi-particles indicates that our hybridization has to be between conduction electrons and a non-Kramers doublet. And if we explore the consequences of that, with in particular non-Kramers doublet for uranium, ruthenium 2, silicon 2, a lot of very interesting things pop out that are consistent with uranium, ruthenium 2, silicon 2. So the key feature of this hybridization is that as it mixes half integer and integer spins, this has to be a spinorial order parameter that breaks double time reversal symmetry in a different fashion from most order parameters that we're familiar with, which are bosonic vector order parameters. So it's different from magnetism. That's why we've invented a new name for it, which is hastatic, which comes from the Latin word for sphere, hasta, and it was not a coincidence that we picked the Latin word that starts with H. Yeah, so it explains many features of an order in uranium to silicon 2. And one of the key predictions that I want to discuss a little bit further is that we break time reversal symmetry, and so this implies a tiny staggered magnetic moment. And at this point, there's now been at least 3 neutron experiments that have ruled out moments larger than 0.0007 for magnetons. However, there are indications from various NMR and USR measurements that are consistent with moments on the order of 10 to the negative 4 for magnetons. So it's possible that the moments are still there, but are a lot smaller than we predicted. This could be explained by having a much lower degree of mixed valency than we considered in our calculation, or it could be a consequence of the fact that these moments are basically in the XY plane and the spinning is very, very weak. Okay, and with that, I think I'm out of time and I will conclude, and I'd be happy to take any questions. Thank you.
I have a question about your model. You described the fluctuation between F1 and F2. But in principle, if you replace F1 with F3 duplet, you will find, right?
It's exactly the same. We looked at that. It's just sort of simpler to explain in the fluctuation set. The physics is the same.
The other question I have is, in your model with F1 and F2, in which you basically Kramers duplet and the whole Kramers duplet into spin, is the kernel of the Hamiltonian must be this duplet, Kramers duplet, right? You start from there. Right?
Sure, from the non-Kramers doublet, yeah.
From the do you start with F2 non-Kramers duplet as a kernel?
As a Kramers
duplet compounds, if you have 0 from the system, the kernel of the Hamiltonian is F0. And you couple F1 limit all and all the other states, but all have a single symmetry. So in your model, do you start with the F1 as a kernel, or the F2 as a kernel, or your conduction electrons?
Oh, I see. So our conduction electrons, I mean, we put in that, okay, so the conduction electron symmetry sort of comes from, well, it's here. So if you put in this gamma 5 doublet and this, you pick a gamma 7 doublet for your F1 configuration or F3 configuration, then that spits out that your conduction electrons have to have these particular symmetries. So
there's sort of becomes a system that F1 plus an extra conduction electron is F2 plus a hole.
Yeah, so you have an F2 and then you add a hole and that gets you to that.
Okay. So, but that means that now you select an F2 hole, ligand hole, which is gamma 5, okay, F2, but the whole thing has a Crowns doublet of the F1, right?
Sure.
Good. But then you can also imagine that this F1 will couple to other F2 states with a leading hole that has the same Crowns doublet, but this F2 could have a different symmetry, right?
Yeah, so you're saying basically it could hop from here to here and then back to an excited state.
And but you could also imagine that the other ones could be the singlet that
Certainly, yeah.
And they could be dominant.
I mean, what you have here is a condo effect, and so the condo effect, you know, as you go to lower and lower temperatures, it becomes more and more dominant. So I would imagine that you would have other fluctuations at high temperatures, but these would not be
Well, I
relevant.
would confess that maybe these so-called F1, F2 states of singlet symmetry could be dominant, but maybe not so relevant for your order. But if you do spectroscopy, you may find them much more weight, right? But maybe the essence of the hidden order is in the gamma 5.
I mean, it is, we do sort of, I mean, the excited states, it's not, you can't really measure the crystal field states.
It's not what the excited states, it's about the mixed state you have in the common state that has a mixture of different F2 symmetries. All of them hybridized to the has a couple of the leading hole, and all of them are hybridized. Crown fields.
Yeah, I mean, in this case, I feel like, you know, it's sort of more physical to start from looking at the non-conformer state and looking at how that hybridizes at low temperature.
I understand for your situation you want to fix the hidden order problem, but if you look at, like, let's say, the calculations of a cochlear, he wants to be quantitative, right? And he may find the other ones to be, let's say, more weight, but maybe not relevant.
Well, I mean, his theory finds that you have two singlets as your ground, right? Which actually, if your temperature is above that splitting, your condo effect doesn't necessarily know that those are two singlets rather than a non-conformist doublet.
Good try.
Similar question. So what kind of experiments do you get from your theory and how does it compare to experiment?
So that's, unfortunately, that's a parameter that we input. So, you know, we don't, it's a sort of qualitative theory rather than quantitative. So we put in the epithelial valence. For the calculations that I showed you, we put in around 20% valence at zero temperature. And this will change, of course, with the temperature. In our theory, which is totally mean field-like, the electron valence purely 2. Above the hidden order and below the hidden order will then decrease from 2 to like 2 minus 0.2.
Gush.
Spectroscopic observations, right? So first of all, application of magnetic field on Z-axis. You would expect that the gamma 5 splits.
Yes.
And you should see spectroscopically the excitations.
Yes. If you're
Experiment
above
is
the
done,
hidden order
they are not
temperature.
seen. The
Are
second,
these measured above the hidden order temperature? Because below the hidden order temperature, the condo effect is set in, and so you can.
no, it doesn't matter because that's the condensate. The gamma 5 is still split, and you will see below hidden order. Above hidden order, everything is fluctuating. Let me go there. So you would expect the fluctuations be in a quadruple channel.
Yeah, there would be fluctuations.
And the fluctuations are indeed strong and very well observed, starting from last Cooper's work of with Brian goes back in 88, right? And it's an A to G channel, a gamma 2 channel.
Right.
And there's nothing in the gamma 5 or other quadruple channels.
But the A2G is so JZ is also in the A2G channel, which is the C-axis.
JZ is exactly a 2G channel, but it's
Right.
not that which is in gamma 5.
I mean, it's one of the components of gamma 5. So, I mean, the JZ.
JZ is gamma 2.
If you're looking at your order parameter being sort of in this, okay, so.
JZ is gamma 2.
So- Okay, so what we're looking at is we're looking at excitations from this gamma 5. So if you're looking spectroscopically, you're looking at excitations from gamma 5 to other states. So they don't have to have the gamma 5 symmetry. So they can.
JX and JY are in gamma 5. JZ is
Yes.
in gamma 2.
Yes. That's true, but the excitations that you're looking at when you go from gamma 5 to another state are not going to be gamma 5 excitations. They will have a different, they can have a different symmetry. They will have a different symmetry unless you're going from gamma 5 to the gamma 1 singlet state. So you don't have to, you can have excitations that go from gamma 5 to, I don't know, some other crystal field
And
state.
how do you get it in an antisymmetric channel? So if you start from gamma 5.
This is going to be some specifics of crystal field theory. We can talk about it afterwards.
Exactly. We have other
I have a very
questions.
simple question.
Sorry.
I just want to understand the order parameter which is in the plane. So is it kind of a superposition of x plus I, x, y or something like that? Is it rotating in the...
So in our theory, it's picked a particular direction. So our conduction electron moments are all, our total moment is along a 45-degree angle in the plane from the x and y axis. But the pinning of this is extremely weak. So, yeah. So I think if this theory applies experimentally, you might not see it into these directions.
Do you have expect fluctuations due to space-based sort of order parameter?
Probably, yes.
Anything like that seen at all?
Uh,
How would you see that parameter?
so, I don't have a particular, I don't have a good answer for that. I think one of the consequences that you would not see this moment that we predicted in the plane.
T2 or is it O1?
So it's, okay, so the moment is like basically a C4 moment, but it's very, very close to being O1, or E1. So the pinning is really tiny. So I think if you're at high temperatures, which would be within the de Noort phase, it would be like an XY moment.
So there's nothing in the lattice that produces it from U1 to...
Oh, there isn't. I mean, it feels the fact that you have a tetragonal symmetry. It's just very, very weak.
Okay.
So,
Last question.
Okay. If I write a gamma 5 pseudospheric orientation XY plane,
okay,
so it's non-magnetic,
sure.
and I apply a GC operator like the Robin excitation matrix on the C, that will fit the orientation of the pseudospheric, I understand. It will flip it in the XY plane, not in the C movement, but
Okay.
is that expected to be a gap excitation or not?
In the ignore state?
Yeah, the question is, does the local orientation of the pseudospinner, you say the pseudospinner is...
So the pseudo-spinner is not a gamma, I guess the pseudo-spinner is like a gamma 7, basically.
Is it, well, you have...
So the spinner is the excited state.
Well, you have a spinner based on gamma 5. And
We
if
do.
the expectation value is the orientation of that
That's-
site, does that have a level 5 orientation? Or is
So
it-
the expectation of the gamma 5 moment in the Hastatic order phase is 0. There's no moment in that phase, and it is sort of wrong to think about.
Right, it's sort of like a singlet, I guess. There's no.
I mean, it's a condo singlet, essentially, right? That's what it's become in some sense. I mean, it's a complicated condo singlet in that it has some spinner characteristics, but those are not from the gamma 5, those are from the excited gamma 7 state.
What application of the field?
Well, I think this is a very, very, very lovely talk, and it's a very enthusiastic section that I think we should reserve further questions to
Yep.
later.